Class 10 Mathematics, second session of Chapter 1, Real Numbers. In this session, I will be explaining the remaining questions of Exercise 1.1, Application of Euclid's Division Lemma. So, we can move on to that.
Question number 1 of the first exercise, exercise 1.1, is already solved in the last session. And question number 2 will be solved after question number 3 because question number 2, 4, 5 are of the same kind. Now, question number 3. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So here we need to make the members of the army contingent 616 and the army band 32 members into columns. So they must march one behind another. That means the number of columns must be same. So the number of columns, the number must be a factor of 32 and it must be a factor of 616. That means we need to find the common factors. But we have here maximum number. That means it should be a highest common factor. The highest common factor means HCF. So we are going to find HCF of 616 and 32. Now, which method we'll use now? So we have different methods because already we learned Euclid's division algorithm in the last session. And the coming session, there is another method, factorization method, which you already learned. We'll revise again. It is also there in this chapter. So in this question, it is not specified which method you need to use and what you need to find. So you can use any method to find HCF. But here I'm using Euclid's division algorithm because we need to master on it. So we know that in last session we studied. So to use Euclid's division algorithm, we need to find the biggest of 616 and 32. We know 616 is the biggest. So it can be written as 32 times a number plus the remainder. So 32 times 9 equals 608. So the carryover will be 8. And we'll look for the remainder, the last number is 0 or not. We know that it is not 0, so we'll continue. So we'll take the divisor of this line as the dividend of the new line. So 32 equals the remainder of the previous line will be the divisor of the new line. So it is 8 times, we know 8 times 4 is 32, right? Plus the remainder will be 0. So we'll stop since the remainder is 0. Once the remainder is 0, the Euclid's division algorithm is stopped. And we'll look for the divisor or the remainder of the last line. Both are same. So HCF equals 8. HCF equals 8. So they can make into 8 groups. 8 columns, so 616 and 32 have the highest common factor 8, so they can make 8 columns of army contingent and army band, so they can march one behind another. So the answer is 8 columns. Okay, so we'll move on to the next question. It is an example question of the textbook. Show that every positive even integer is of the form 2q and that every positive odd integer of the form 2q plus 1, where q is some integer. Here we will use Euclid's division lemma. What is Euclid's division lemma? We know that for every positive integers a and b, so it can be written as a equals bq plus r for some positive integer q, and where 0 less than or equal to r less than b. So this is the Euclid's division lemma. So we'll use Euclid's division lemma to prove this one. So let a be the any positive integer. We'll take let b a be any positive integer. Any positive integer. Okay. And for B, we need the Euclid's division lemma start with two numbers, two positive numbers, A and B. So we need B also, but here we will give a value for B. So let B equals 2. Why 2? Because we need to show that the positive even integer is of the form 2q and odd integer is of the 2q plus 1. So you can see 2 with the q there. So from this question, we'll identify the value of b equals 2. So this Euclid's division lemma can be rewritten as a equals 2q plus r where 0 less than r less than 2. So what are the values of r then? So r can be 0, it can be 1, it cannot be 2 because r less than 2. So we'll give these values here. This will become a is equal to 2q plus 0. 2q plus 0 is 2q, or a will be equal to 2q plus 1. So these are the two options because we gave r is equal to 0 here. R is equal to 0 and R is equal to 1 are the two options. So we used R is equal to 0 here. So A is equal to 2q plus 0. 2q plus 0 means 2q, or A is equal to 2q plus 1. The R value is given as 1. So when a number is a multiple of 2, it is an even number, and a multiple of a even number plus 1 is always an odd number. So every positive even integer will be of the form a equals 2q, and every positive odd number will be of the form a equals 2q plus 1. So now we'll move on to the next question, question number 2. So this is same as the previous example. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So all these, I said you, all these type of questions will use, for all these type of question, we'll use Euclid's division lemma. So we know that Euclid's division lemma is for two positive integers a and b. So we need two positive integers. So for that, we need a and b here. So let a be any positive integer. Let a be any positive integer. Positive integer. And we need b, right? So we look at the question now. It is 6q plus 1, 6q plus 3, 6q plus 5. With the q, 6 is coming. So we'll select b is equal to, let b is equal to 6. So using Euclid's division lemma, so any positive integer a can be written as bq, that is 6q plus r, where 0 less than or equal to r less than 6. So what are the values of r? That means r is equal to 0 or 1, 2, 3, 4, 5. It cannot be 6 because r less than 6. So we have these many options. So we'll substitute one by one. So we'll start with r is equal to 0. So when r is equal to 0, a is equal to 6q plus 0, that is 6q. And 6q can be written as 2 times 3q. And whenever we get a multiple of 2, it is an even number. So this is even number. This is even number. Okay, multiple of 2 will be always 2q, a number of the form 2q, 2m, anything, 2n, all are even numbers. So it is an even number. Next, we'll substitute r value. R value is 1. So when r is 1, a is equal to 6q plus 1. And we already got 6q is an even number. So an even number plus 1 is always an odd number. So when r is equal to 1, this is an odd number. Okay. Now, next we'll substitute r is equal to 2. R is equal to 2. So we'll get a is equal to 6q plus 2, which can be written as 2 times 3q plus 1. As said, When we get a multiple of 2, it is an even number. So it is a multiple 2 times anything is a even number. So this is even. This is even. And now next option, r is equal to 3. So we'll select r is equal to 3. So this will be a is equal to 6q plus 3, which can be written as 6q plus 2 plus 1. So 6q plus 2, we already got 6q plus 2 is an even number, and even number plus 1 is an odd number. So this is odd. Okay. Now next option. So we have r is equal to 4. R is equal to 4. So when r is equal to 4, a can be written as 6q plus 4, which can be written as 2 times 3q plus 2. 2 times 3q plus 2. So we know that a multiple of 2 is an even number. So this is an even number. Now the last option, r equals 5. R equals 5. So here a can be written as 6q plus 5. It can be further simplified 6q plus 4 plus 1. So 5 can be split into 4 plus 1. So 6q plus 4 is an even number from the previous line. So an even number plus 1 is always an odd number. So this is an odd number. So now look, which are the odd numbers here? So when r is equal to 1, 6q plus 1 is an odd number. When r is equal to 3, 6q plus 3 is an odd number, and r is equal to 5, 6q plus 5 is an odd number. So every odd number will be of either of the form a equals 6q plus 1, or a equals 6q plus 3, or a is equal to 6q plus 5. Okay, we proved it. Question number 4 of the exercise 1.1. This is also almost the same, but a small difference is there. Here, the question is, use Euclid's division lemma to show that the square of any positive integer, the square of any positive integer. So here, we need to find the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Here also, we'll start with the two numbers a and b. Okay, so we'll start, we know we need to use Euclid's division lemma. For Euclid's division lemma, we need two numbers a and b. So let a be any positive integer. Let a be any positive integer. Positive integer. And b is equal to, we'll select a value for b. So we look at the question. So it is 3m plus 1. So we will get it is 3. So we'll give b equals 3. Okay. Now using Euclid's division lemma, a can be written as a is equal to 3q plus r, where 0 less than or equal to r less than 3. So what are the values of r? So that means r is equal to 0, 1, 2. It cannot be 3. So these are the three values. Now we'll start with r equals 0. So when r equals 0, a is equal to 3q. But the question is not a, square of any positive integer. A is any positive integer. So we need to square it. So we need to find a square. So this is 3q the whole square. So 3q the whole square, we know that it is nan q square, which can be written as 3 times 3q square. Why we are taking 3 out? Because we need to show it is of the form 3m. 3 times a number. 3m means 3 times a number, where m is a number. So m is a number. So here 3 times 3q square. We know q is a positive integer. So q square is a positive integer. 3 times q square is another positive integer. So it can be written as 3m, where m is equal to 3q square. So 3q square is a positive integer. So m is a positive integer, 3m. Okay, so now we'll go to next option. So r is equal to r is equal to 1. When r is equal to 1, what will happen? So we know that a is equal to 3q plus r. So 3q plus 1. We need to find the square because in question it is a square of any number. So a square is equal to 3q plus 1 the whole square. So a plus b the whole square form. What is a plus b the whole square? Please remember a plus b the whole square is not a square plus b square. It is a square plus 2ab plus b square. So this can be nan a square 3q the whole square, that is nan q square plus 2ab, 2 times the first term times the second term. So 2 times 3 is 6, 6q times 1, so 6q plus b square. B square is 1 square. Now from the first two terms, we can select 3 as common. So it will take 3. So why we are taking 3 common? So we look at the question. See in question. So 3m, 3m. In both the terms, there is 3. So that's why we are selecting 3 common from the first. We cannot take 3 from all the 3 terms. So we'll select 3, take common from the first two terms. So 3 is taken common. So the remaining will be 3 times 3q square, because 3 times 3 is 9, plus 2q plus 1 outside the bracket. So it can be written as 3m plus 1. What is m? So I'm replacing this 3 square plus 2q as m. So where m is equal to 3q square plus 2q. Okay, so it is of the 3m plus. So I found there are some students will stop here because we got so the numbers are of the form 3m or 3m plus 1, or we got here 3m 3m plus 1. We cannot stop here. We need to check for 2 also. We have 3 values for r is equal to 0, r is equal to 1, r is equal to 2. So we must continue. So we'll give r is equal to 2 now. R is equal to 2. So we'll continue. So what will happen? So A is equal to 3q plus 2. We'll square it. A square is equal to 3q plus 2 the whole square. So using a plus b the whole square, so we'll get nan q square plus 2ab. The middle term is 2 times the first term multiplied by the last term. So 2 times the first term, 3q. So 2 times 3 is 6 into the last term 2. So 6 times 2 is 12. So you'll get 12q plus the square of the last term, that is 4. 2 square is 4. Now we cannot take 3 common from all the terms. So, and this one is the last term is more than 3. It is 4. It is more than 3. So what we'll do is we'll simplify this further into nan q square plus 12q plus 3 plus 1. And from the first 3 terms, we'll take 3 common. So it is 3 times 3q square plus 4q plus 1 plus 1. And all the bracket terms. So this complete 3q square plus 4q plus 1 will substitute as m. So we can write this is equal to 3m plus 1, where m is equal to 3q square plus 4q plus 1. So you can see that the square of any positive integer is either of the form 3m or 3m plus 1. Again, we are getting 3m plus 1. So we are not getting any third option. So the square of any positive integer is either of the form 3m or 3m plus 1. That's the result. That's all for now. I will move on to the homework section. Now it is the practice time. So take your pen, book, and do this question. Okay. And this is same as the first question of today's session. And if you have any doubt, please go back and watch that session again. That's all for today. Bye.